Methods of science and technology. Now this image is of a 3D printed ear. 3D printing holds the promise of changing the healthcare industry for the better by offering products such as smarter drugs and prosthetics. Now, in fact, this technology is already happening. Researchers from various leading universities have 3D printed functioning human organs. This could help to address the shortages of donor organs around the world, and especially in the United States. Technology is the application of science to solve problems. Because technology finds solutions to practical problems, new technologies may have major impacts on society, science, and industry. Bridges are structures that span horizontally between supports, and their function is to carry loads. However, no matter the size or the design, the same engineering problems must be overcome in every bridge. These include the supports must be strong enough to hold the structure up. The span between the supports must be strong enough to carry the loads. So therefore, all bridges need to go through the process of technological design. Technological design is similar to scientific investigation. Both processes rely on evidence and reason, and they follow a logical sequence of steps to solve problems or answer questions. Now, the technological design process can be broken down into a series of steps shown here. And just like the scientific method, some of the steps may have to be repeated, and sometimes the steps may not always be done in the sequence shown, but these are good guidelines to look. Here we're looking at step 1, we identify the problem. Once we do that, now we can go and research the problem. Once we have a good understanding of the problem, we're going to move to step 3 and generate possible solutions. And once we decide on what is that best solution that we think can help this problem, we're going to select that problem, and then we're going to create a model of the solution. When we do this, we then have to go into the testing phase of step 6, and we need to start testing the model to see if we were correct. And maybe once we start testing, we're going to have to see, things need to get refined. We need to kind of go back to the drawing board and maybe fix a few things here and there. And then we retest the model until we get to a point that we feel that model has gone ahead and fixed that problem or helped with the solution. When we're done, then we communicate the results and either share the results that, yes, this model was successful for this problem, or this model was not successful, and then give evidence to support our results. Now, often the main challenge in technological design is finding a solution that works within the constraints or limits of the design. All technological designs have constraints. When we're talking about physical design, these constraints include factors such as natural laws and maybe the properties of material. Okay, here we're looking at the drone and these concept cars, right? Now, when we're talking about those, we know we have to get these materials, and we have to make sure that these drones can fly. We have to overcome those. But then there's also social design constraints, and these include factors such as how easy something is to use, the safety of it, the attractiveness of it, and then of course there's cost. Okay, so take for example, we have this DSX concept car here, and this is produced by a luxury French brand called DS. Now this concept car is designed to show what the company thinks is a hugely powerful all-electric self-driving machine might actually be like, right? The concept car is called a development accelerator, and this is what the DS design director says that it is. This helps test new technologies that we might imagine for the future and accelerate their development, right? So usually concept cars don't come to fruition because of the overwhelming cost to create them. But making these concept cars sometimes bring us to parts that work, and then we can use those in future technologies. Now, all technological designs have trade-offs because no design is perfect. Choosing the best design involves weighing the pros and cons of different options that we just talked about. Now, when we do science, a lot of times scientific work often requires calculations. Now, calculations may include like converting units, say from degrees Fahrenheit to degrees Celsius, or sometimes you need to use basic math skills like multiplying length times width times height to calculate volume, or you may need to plug your data into a formula such as distance and time to calculate speed. This image here is a bacteriophage, and it is a virus that infects bacteria. And it cannot be seen with the naked eye because it is so small at 0.00000008 meters. There are many quantities that are extremely small like this, or the opposite, some are extremely huge, right, with lots of zeros on the end. So these quantities are made up with numbers with lots of zeros, and this is where scientific notation comes into play. Scientific notation is a way of writing very large or very small numbers that use exponents. So numbers are written in this formula. A equals 10 to the B. A is going to represent a decimal number, and the letter B stands for an exponent or power of 10. So for example, the number 500 is written in scientific notation as 5.0 times 10 to the second, right? It's going to move that decimal point. Or in the case of the virus, 0.000008 is written as 8 times 10 to the negative 7. Now, it may seem a little tricky, but it's just a matter of counting the decimals. Follow the steps here to convert to and from scientific notation. In step 1, we're going to move the decimal point left or right until the last non-zero digit. Then, step 2, you're going to count how many places you moved that decimal point. And then third, if the decimal moved left, B is positive. The decimal moves to the right, then the B is negative. Okay, I think we have gotten through everything in this section, so it is time for you to show what you know.